So this is going to be my talk at CCS next week. Two things before I start. The slides need to be modified a little bit more. In particular, there is an animation that is missing. I'm going to try to make it appear before my presentation next week. So I'm going to talk about Onion Ring ORAM, which is our new proposal. It's an efficient constant bandwidth ORAM scheme, which uses FHE to improve an eviction phase inside, and in particular the FHE scheme we use is the level TFHE. So it's a working collaboration with Hao Chen from Microsoft Research and Ling Ren from University of Illinois. So I'm going to start by introducing a little bit the scenario, then I will give you a bit of background on the two main techniques, which are Onion ORAM and TFHE, and then I will describe how we solve the problem, and I will give you some implementation results, analysis, etc. And I will conclude with some future work. Okay, so since we're talking about ORAM, what is ORAM? So ORAM, Oblivious RAM, was proposed by Goldrake and Ostrowski, and it's a cryptographic protocol that allows you to hide the access path of your data, which is stored encrypted into a remote server. So the server acts as a storage unity, and you want to access your data. In particular, the client would like to read and write this data without leaking any information. The problem of ORAM is that there is a huge communication. So if you have at least n entries in your data set, there's going to be a logarithmic blowup, bandwidth blowup in the communication. So of course, now this logarithmic bandwidth blowup is asymptotically optimal. So if you want to really reduce this communication, you have to think a bit out of the scheme. And this is what they did in 2016 in Onion ORAM. Devadas is co-authors. So they proposed Onion ORAM, which is now working in the server computation model, which means that the server is not only a storage place, but has also computational power, which is actually the reality. Now every server has large computational power. And in order to reduce this communication, they decided to use homomorphic encryption. So ask the server to do homomorphic encryption computation in order to reduce the communication. Unfortunately, this work is only theoretical, it's not practical at all. So what we did in our proposal is to propose Onion Ring ORAM. This is not a RAM session. So what is Onion Ring ORAM? Is a mix between Onion ORAM and the TFHE scheme. So it's efficient, the first efficient constant bandwidth ORAM scheme. And thanks to the fact that we use some TFHE techniques in order to improve the homomorphic computation on the server side. And in particular, we propose an efficient homomorphic permutation protocol by using some TFHE techniques. And what we show in the paper is that we improve Onion ORAM at least by 3 orders of magnitude. And also, when we compare to other ORAM-based scheme like Ring ORAM or Path ORAM, which are logarithmic, which is logarithmic blowup, we definitely outperform them, in particular when we have network throughput, which is quite limited. Okay, so let's start with a little bit of background. So what is Onion ORAM? As I said, it's an ORAM scheme. We work in this scenario where we have a client which is trusted because he's the owner of the data, and the cloud which is untrusted, but we work in the honest but curious model, so all the parties should follow the protocol. So the cloud stores the data of the client encrypted by a public key. Of course, the client owns the secret key, and every time the client wants to access the data to read it or write it, it sends a request. So the request is composed by an address, which is the location where the data it wants to access is in the data set, an operation, which is read or write the data, and the actual data encrypted. Of course, if he wants to read only, he's not going to send any data because he wants to receive some data. Okay, so How the data is stored on the server side? It's stored in this way, like with a binary tree, in a binary tree manner. So the binary tree is composed by L levels, which strictly depend on the number of data that is stored in the dataset. And in every node, which is also called bucket in the tree, is divided in Z slots. And every one of these slots contains a block, which can be a logic block, so containing actual data, or a dummy block containing just random stuff or encryptions of 0. And these blocks have size b bits. Every logic block, so every block containing actual data, is randomly mapped into somewhere in the tree, and the client stores locally those paths. So the client knows exactly where the logic blocks and where dummy blocks are in the tree. So when he wants to access, and here is the missing animation that will appear at some point, so it does the following. So imagine that he wants to access a block which is in this part in here. So it knows how the mapping of the dataset is done. So he decided to choose a path that brings him to this block, which can be a path that goes from a leaf to the root all the time. And then he sends this path to the server. They interact by doing some, they extract this desired block by doing some private information retrieval technique. And then at the end of the protocol, the block containing the information he's looking for is going to be added into the next slot, empty slot in the root bucket. The only problem is that if you start doing many requests, of course, the root bucket has limited space, so it's going to start be filled. And so after a number of access, which needs to be limited by the large, the size of the root bucket, you need to perform an eviction phase, which is a procedure that allows you to empty the root by moving the information back to the leaves. And this eviction phase is a bit costly. Okay, so the second element that we use in Onion Ring ORAM is the TFHE scheme. So I'm not going to give that many details. So TFHE is a fully homomorphic encryption scheme that was proposed in 2016. It uses a ring variant of the GSW scheme proposed by Gentry, Shai, and Waters in 2013. And its security is based on the learning with error problems and on its ring variant. So TFHE is implemented and available online, so we use the public implementation in our tests. So TFHE comes with two modes: a fully homomorphic mode, which means that you can perform as many operations as you want because you do bootstrapping very often, and a leveled homomorphic mode, which means that the number of operations you can perform is limited by the choice of your parameters. So for our Onion Ring ORAM, we didn't need any bootstrapping. Everything we do can be supported by leveled operations. So in particular, we're going to use two ciphertext types proposed by TFHE. The ring LWE ciphertext, which encodes torus polynomials, where torus means reals modulo 1. The polynomials are modulo x and +1. And the ciphertext look like two polynomials. The first one, which is chosen random, and the second one, which is just equal to the product between the random initial polynomial times the secret key plus some error plus a message. And ring LWE is additive homomorphic, so you can do linear combination between ring LWE ciphertext. In order to perform multiplication, which is going to be needed, we're instead going to use ring GSW, which is an extension of ring LWE. It's a bit more complicated the way we create the ciphertext. In fact, we have an addition between a matrix Z, which is a list of encryptions of 0, ring LWE encryptions of 0, like this kind of encryptions, and a message, which this time is an integer polynomial, not a torus polynomial, and this gadget matrix, which is public one and which is important because it allows us to do the multiplication. We can ignore a little bit the details. The important thing is that in ring GSW we have additive and multiplicative property. And more than this, it's interesting to say that in TFHE there is also an external product between the two ciphertexts proposed. So the ring GSW, which is the large one, and the ring LWE, which is the small one. And this external product gives us a ring LWE ciphertext. So the noise growth in this operation is additive, so it will grow very slowly compared to other schemes. And we use in particular the external product to define this mux gate, which is going to be essential in the construction of the homomorphic permutation. So the mux gate is simply a selector that takes in input a large ciphertext containing 1 bit, the selection bit, and the gate outputs D0 or D1 depending on the value of this bit. You can imagine it just as a selector gate, as a multiplexer gate, but homomorphically evaluated. So we're going to use this gate in particular to build the homomorphic permutation that allows us to improve the eviction phase. Okay, so how does it work, our actual construction, the Onion Ring ORAM? So it's divided in 3 main parts. There is an initialization phase, there is an access phase on which the client does the request, and then after a certain number of accesses, as I said at the beginning, we need to do the eviction to empty the root. So in the initialization phase, the client generates the public and secret keys. In particular, it's going to need the ring LWE keys for the homomorphic part and AES keys. And the server on its side, it initializes the entire tree with just dummy blocks, so no information. And in particular, the dummy blocks are going to be just ring LWE encryptions of 0 that it can produce because it knows a ring LWE public key. Then it comes the access phase, so where the client actually wants to access his data, so read or write. So instead of using PIR operations like in previous proposals, we decided to use some ring LWE homomorphic encryption by combining permuted buckets. So the idea is that in the entire tree, there are some logic blocks encrypted as AES encryptions inside a ring LWE encryption, and dummy blocks, which are just ring LWE encryptions of 0. So when the client wants to access a specific block B, he knows where this block is placed in the tree. He just checks in his local mapping where this block B is in the tree. And he chooses a path to go to this block B. And the path is specific because he tries to choose in every block in the path a dummy block, and just the block he wants to access is not dummy. So what I mean is, like, imagine there is a path from the root, from the leaf to the root. It chooses 1 block per level, and all of these blocks are dummy, so encrypt 0, but the block is looking for. So what does the server do to answer this request? It just adds together, thanks to the ring LWE property, those blocks that are asked by the client. So at the end, this is going to be a ring LWE encryption of the AES of the block is asking for. And then the slots, the client takes into account the fact that those slots have been already touched, so he cannot choose them anymore. And he puts the block he asked for in the root bucket. So, of course, after a certain number of accesses, this root bucket is filled. So we need to do what I said before, the eviction. So how does the eviction work? So the main goal is to empty this root and to move data on the top of the tree. So the eviction starts from the root. So what the client does is that he downloads the root, he decrypts everything, and he re-encrypts the data and sends it to the server. Of course, he encrypts with AES, the server can re-encrypt with ring LWE. And then, so the server computes, encrypts with ring LWE, and then they perform part is going to be the actual blocks, and then it completes with dummy blocks is needed. And then they perform an homomorphic permutation in order to shuffle the stuff in the root. So the homomorphic permutation I'm going to describe in the next slides. So after the eviction has been done in the root, we need to move up to the tree. So we're going to perform a triplet eviction. which is in practice, you take from the root, you have always every bucket has two children. So you consider a triplet where you have the parent bucket and the two children. And what the triplet eviction does is just it moves some information from the parent bucket to the two children, completes with some dummy blocks, and repermutes again. So this continues this way until we reach the top level where we have only the leaves. And in the leaf bucket, what happens is that the client, now this is performed after many homomorphic operations, so the noise is big. So the client just downloads everything, decrypts, re-encrypts, and sends it to the server. So we can keep low noise and we can continue without doing actual bootstrapping. Okay, so as I said, we're going to use, as you see here, we have homomorphic permutation in the root eviction, we have multiple homomorphic permutation in the triplet eviction, and we have also homomorphic permutation in the last round. So how is the homomorphic permutation? How does this homomorphic permutation work? It's actually very easy. It's just a Waxman network, which is just a concatenation of swap gates. So a swap gate take into in input a swap bit that can be 0, 1, two elements to swap. So if the bit is 0, nothing happens. If the bit is 1, the buckets are swapped. Of course, we do everything here by using homomorphic encryption, and in particular the MUX operation of TFHE. So we're gonna, the X elements are gonna be encrypted by using ring LWE, so the vectors in my previous slides. And the B bits, which are the swap bits, are gonna be the selector part. So they're gonna be huge ring GSW encryptions. So now this huge ring GSW encryption can be a problem because the client needs to send to the server the swapping bits to communicate which kind of permutation he wants to perform. So in order not to have a large communication overload, we decided not to send in a trivial way just the ring GSW encryption, so those huge matrices encrypting just a single bit, but to send those bits encrypted together in a small ring LWE ciphertext, and then to perform on the server side an homomorphic extraction. So in practice, the input to that the client sends to the server is a ring LWE ciphertext, which encrypts together multiple swap bits, and then the server on its side will extract those bits and convert them into ring GSW. And this operation is just a mix of key switching and external products in a smart way. And that's it. So a few comparisons. So if we compare this homomorphic expansion we propose with the naive one, we observe that actually the communication is highly reduced. Of course, one is naive, one is, well, whatever. Also, we decided to compare our technique by using TFHE with other similar techniques but using different homomorphic schemes, such as somewhat homomorphic encryption, BGV in particular, and the additive scheme by Damgard and I don't remember the J. Sure. Thanks. And we observed that actually our techniques is about 2.5 better than the BGV and about 4 times better than the additive one. Before I conclude, so a few parameters for our implementation. So for the TFHE, we use the experimental TFHE library, which is available on GitHub. So we have rings dimension of 2048, which is a noise which has standard deviation 2 to the power of minus 55. And we achieve about 120 bits of security according to the LWE estimator. And another important thing that we did is that we reduced the expansion factor by packing together many elements. So in a ring LWE, we can encode actually 3 kilobytes of data. And for ORAM instead, we choose 2Z, because actually the buckets are 2Z large, equal to 508, which means that every bucket contains 16 ring LWE encryptions. The number of maximal accesses before an eviction is about 2050. So we have a 2 to the minus 80 failure probability. And we tested for 3 different size of blocks, about 300, 700 and kilobytes and 1.5 megabytes. And we did our experiment in a virtual machine, Azure virtual machine, with 8 cores. And we decided to use 8 cores for the server computation and just 1 core for the client computations on the client side. So here I have 2 comparative tables. The first one is actually just to measure the blowup compared to previous ORAM techniques, such as ring ORAM and path ORAM. We of course are way better than path, and compared to ring, we are 35% better in terms of bandwidth blowup. But actually, the second one is funny, interesting. So at the beginning, when we submitted, we didn't put this table. It was asked by one of the reviewers. And it's actually interesting because he asked us to estimate the monetary cost in using ring ORAM, which was the best, previous best, and our scheme, Onion Ring ORAM. So why the monetary cost is interesting? Because we can actually estimate what is the cost of the communication and what is the cost of the computation. So the point is that ring ORAM doesn't have any computational cost. It does only communication. The communication is big, but it does only communication. Onion Ring does communication less than ORAM, but there is a computational cost on the server side. So what we did is that we just took the Azure server, and we take the prices they proposed, and we try to estimate how much would it cost to use our scheme or the previous schemes. And we observed that we actually have a 40% gain in terms of money. That's it. I found it interesting as a comparison. And the last but not least, also we compared the latency, so the communication. We observed that we are way better with low throughput networks. So we are way better than ring ORAM, and when the throughput increases, the difference starts being less interesting. So to conclude, I will summarize a little bit what we did. So we proposed the first efficient single server. I didn't say it before, but it's single server. ORAM with constant bandwidth blowup, so constant communication. So the scheme is based on previous ORAM, Onion ORAM scheme and on the TFHE homomorphic scheme. The efficiency on the server side is due to the fact that we use an intelligent homomorphic permutation protocol and extraction. And we observed that the latency compared to previous ORAM techniques is way better, in particular with low throughput networks. So as future works, a few of them. The first line is actually not really a future works. It's more like something that we know that we can use to improve. So in particular, if we want to reduce the size of the LWE ciphertext, the fresh one, when we send them into the network, we can actually use PRG to generate the random part or use some modulo switching if the noise allows us. The important open problems are the one that the reduction of the bandwidth blow up, which is still quite large. We think that we can do something more on this. And since we worked on the honest but curious model, of course, we would like to extend the security into a malicious setting. And I think that's all I wanted to say. Thanks a lot for your attention.